Good afternoon to all of viewers. So, today I will talk some brief outlines of the fluid bed reactor and try to cover some design aspects of a fluidized bed reactor, especially the bubbling fluidized bed reactor. All of you know about the fluidization because you must have read in your undergrad mass transfer courses, and you know that the gas, if it is a packed bed and you give the flow at different velocity, then up to a certain superficial gas velocity, there will not be any kind of the bubbling, or the bed will be static, right. The solids will remain at a stable condition in the bed, but when you increase the velocity, then there will be a kind of more and more voids, right, and then the bed starts something like a fluid kind of state, or there will be a kind of bubbling inside the bed. So, this principle, which is based on some gravity force acting downward, then buoyancy force is acting and some drag force is acting on a particle. So, this principle has been used in the reaction engineering or reactor design or catalytic reaction engineering, where the solid is the catalyst, and depending upon the operation, we can have a kind of a CSTR or mixed bed reactor, and the gas can be bubbled through this catalyst, or vapor can be bubbled through this catalyst, and there can be good contact between the gas and solid, and there is a kind of back mixing in the reactor. So, that basic concept is something like where you have a fine powder or fine solid particles, and they are transformed into some kind of fluid like state by using some gas or vapors or liquid. So, depending upon the flow, you can have different situations in a bed. So, which can be seen here, that this is just like a fixed bed when your velocity is relatively low, superficial gas velocity is relatively low. So, that time the weight of the solid is more dominating compared to the buoyant force, right, and viscous force. So, all these what you have done in your Stokes law, and depending upon that Regim's Reynolds number and pressure drop equations in the fixed bed and fluidized bed equation. So, this is a static condition where you have a minimum voidage in the bed. So, bed voidage is almost, and if it is a very fine powder, it will be low, right. So, but when you increase the velocity, the bed starts like this, a bubbling, a kind of where the particles are moving up, right, and you will find more and more voidage between the bed. So, gas fills the interstitial space between the solid particles, there is now a gas, right, and the particles moves up and down. So, that is a kind of bubbling, just like water boils, and you see the droplet goes up and coming down because of the convective currents. So, this is a situation here that you have a kind of bubbling bed, but solids are not leaving the reactor or the column, right. But when you have still a higher velocity, you can have some through flow of solids, like. So, that is the more and more movement. So, your voidage between the particle is increasing. So, your pressure drop will be low now, right. The contact between gas and solid may be better, but there may be a kind of situation where you have a slug flow condition, the pocket of solids and then gas leaves, kind of channeling may appear, right. So, that is a kind of turbulent fluidized bed, and when you have still the particles are very fine. So, all it will depend on the size of the particle, that is first thing, and I told that there is a buoyant force, there is a viscous force, gravity force. So, it means it will depend on the viscosity of the medium, it will also depend on the density of the gas, and of course, the superficial gas velocity, which is very important. So, it means something like a rho s minus rho g, if I talk density of the solid and density of the gas. So, that will also be a parameter which will affect, and size of the particle is very important, right. So, you need to characterize these things before looking the type of fluidization behavior, and also it will depend on the property of the solid. So, the solid may be cohesive type solid, just like floor, right, it may not fluidize easily. So, that is what a different characterizations or classifications of the solids, what we known as Galdard chart. So, that is known as Galdard classification, basically something, a classification given by this Galdard. So, known as Galdard classification. So, basically in this classification you have something like A, B, C, D. So, we have categorized the solid in different category A, B, C and D. So, which may be difficult to fluidize, right, which may be a cohesive nature in and that will depend. So, depending upon that, if you wish to fluidize, you need to have a rho s minus rho g and as a function of diameter of the particle. So, as the diameter of particle increase, the fluidization will become still difficult. So, this is one. So, it means depending upon the superficial gas velocity, you can have a region from fixed bed and to a kind of system when the particles leaves the bed, right. So, this fundamental thing can be used in a spray tower units where the powder, fine powder is moved from the bottom to the top, right, and it can be used the kind of a conveying also. So, powdered material can be transported through the unit, right. So, that is solid fine and you have very high velocity. So, it is a kind of pneumatic conveying system. So, where the solids are leaving the bed continuously. So, continuously their solids are coming along with the gas and then they are leaving. So, it can be a kind of illustration also. So, it means when you look this kind of system, a bubbling fluidized bed or a reactor which may be a kind of circulating fluidized bed. So, one needs to control the velocity of the solid, right. One needs to control the velocity of the gas. So, basically velocity of gas will decide the particle velocity, right. So, that is important in this case when you have a fluidization. So, the size of the particle is important, viscosity, density of the gas. So, all these becomes very important in order to give a definite kind of fluidization. So, these are also known as circulating fluidized bed because the particle moves up and down and one can have a circulation of the solids within the bed. So, there are some key terminals here or some key terminology in terms of in order to define the different characteristics of the solid and what I was talking a Geldart chart. So, Geldart chart is something briefly I can just discuss here in this, which is a different category here. So, we have rho s minus rho g here and this is as a function of the diameter of the particle. So, you can have different size of the particles like say 50 micron. So, this is generally in the micron unit and it can go up to a level of 100 micron, right, or even higher 200 micron, something like that. So, these are small size particles and this side you have a density of the particle which can be a difference of the density of solid minus gas. So, 0.1 and here it can be up to 5 also. So, the solid density is high and gas density is always low. So, effectively it is the density of the solid which is dominating. So, you can have different kinds of classification or standard curves. So, this is known as a type C which is a cohesive material, this zone. So, this is showing a just like a floor type of material which is difficult to fluidize basically, right. So, lumps goes up along with along with the gas here. So, and then in between we have a kind of B classification, then there is a kind of category D classification. So, overall if you see this, so you have the range now. So, this is your D type, this is your B type and this is your C type, in between this is your A type. So, this is A type. So, this is your cohesive material here. So, which is generally for very fine powder just like floor type of material. So, very small particle size may leave the bed easily, right, if you have high superficial gas velocity. And this side it is the density of the solid and density of the gas. So, depending upon this one can select a definite condition for required for fluidization. So, it means particle size is important, density or physical property of the solid material is important, gas is important and other viscosity of the medium, that is important. So, this is what I am talking a bubbling or a type of arable particles here, right. So, arable particles, this is one classification which is known as where the bed expands and then forms the bubble. So, this is what a good region for CFB, what is known as a bubbling fluidized bed or a circulating fluidized bed. So, I will write it CFB, circulating fluidized bed. So, here in this region at a, so it means some definite size of particle and the density difference, you will have a better situation. Whereas, this is a kind of cohesive system here. So, cohesive system. So, that is difficult to fluidize. So, these size particles which are very fine in one way and they are very difficult to fluidize. Here in this D type, this is known as spoutable and this is a kind of spouted bed, which is for large size particles especially, right. So, basically it is not able to fluidize easily again, right. So, that is just the particles are larger in size, then density is also high, right. So, they are very difficult to fluidize again, right. This is what the zone where the we feel that this is a better way of fluidizing. This is for sand like particles here, right, which can be fluidized under certain conditions. So, this is your category where bubbles grow up and size increase. So, gas bubbles will be there and solids will be surrounded by that. So, this is what the bubbles increase in size. So, when you have higher flow velocity, so bubble will grow up. So, gas bubble will increase in the size, right. So, there are different classifications and this is what known as Geldart chart. And this is generally used for the classification of particles depending upon their degree of difficulty of fluidization. So, A, B, C, D like that we categorize them and the depending upon the size of particle, depending upon the density difference and then we categorize them in different category. And this is the basis for selecting the superficial or minimum superficial velocity required for fluidization also. So, in that the terminology which is generally used, so as I said attrition, because in the fluidization the particles are just moving up, right, and there are the forces acting between the particles. So, particles should have a good kind of attrition resistance. If the material is soft, then it will get crumble and because of that the particle will become smaller in size and they will leave the bed or you will have a loss of the catalyst material. So, that is again important. So, attrition generally refers to the breakdown of particles. The second thing is choking, right. So, choking is again the collapse of a dilute phase suspension into a dense phase flow as the gas velocity is reduced at constant solid flow. So, you have a solid which is moving up, you have a gas which is moving up. So, when you reduce the flow, so what will happen, all the particles will come to one point, right, and that is what you call the dilute phase has gone down. So, it is now has become a dense phase where more particles or cluster of particles are located at one point, right. So, we have a kind of dilute phase where the gas can pass through that and there is a good contact between gas and the solid catalyst and that the product forms, right. So, dense phase and dilute phase. So, these will be there, right. So, if you need a good contact between, so your diameter of the column should also be specified, right, because there should be a good contact between gas and liquid, right, or the gas and liquid or the catalyst gas and catalyst or vapors and the catalyst when they are moving from in the bed. If you are circulating fluidized bed, because I told the degree of mixing is again important and fluidized bed when you have it behaves like a CSTR. So, your conversion may be lower or productivity may be lower. So, sometimes we just enhance the productivity by just recirculating the catalyst in the bed. So, that is again required when you have a cracking reaction and then catalyst activity decrease because of the carbon deposition. So, you need to have that a unit which is designed to send particles around in a loop continuously with no upper interface within the bed. So, the solids are going up, taken to a unit where they are regenerated and then sent back into the system, and this is known as a circulating fluidized bed. Then downer, because the solids are moving up and coming down also, right. So, downer again in the column a point where the particles are made to fall through under the gravity in a co-current. So, gas is moving up and because of the gravity the particles will have a tendency to fall down. So, you have the velocity. So, you are trying to come the pressure drop and find the velocity where the pressure or the weight of the particle should overcome with that velocity, and then the particle will start bubbling or moving up, right. So, this is the point which is required here in this case, and that so downer is the in the column where the particles are made to fall through under the gravity in a co-current gas. So, gas is moving up and particles are falling down, right, and that is the known as downer, and especially again in the fluid catalytic cracking unit, and there are riser and there is a known as downer also. Again distributor, I told that there should be a good contact, right, and that is to be identified through hydrodynamic study. So, we need a good kind of distributor, right. So, distributor is simply a support plate which is at the bottom, which introduce the gas to the bottom of the bed. So, through this the gas is passed to the bottom, right, from the bottom, and so that the good kind of bubble should come, gas bubble should come, right, to introduce the gas to the bottom of the bed and supports the weight of the bed when the it is not in operation. So, when it is a fixed bed type, so through that the solids will stay on that plate, but when it is in movement or operation, then the gas is sparged through that, right. So, it is a sparger basically or distribute. Illustration, again it is a tendency of fine particles to be preferentially entrained from the reactor. So, during that when the particles are smaller in size, they will leave the bed, right, and that is known as illustration. Then again fast fluidization, this is a flow regime where there is a relatively dense suspension, but no distinct upper phase. So, as I said when I was showing the picture different types of fluidization. So, at high superficial gas velocity, so first you will from bubbling fluidized bed it will transform to a turbulent fluidized bed, and then you have a fast fluidized bed. So, basically this is again at higher gas velocity. Then fines are very small particles, especially of the submicron level, right. So, which are less than a micron in diameter, and smallest regular sieve size, that is what considered here. So, small size particles, and they can leave the surface, right, during the fluidization. So, these are known as fines. Interstitial gas, this is the gas which is staying between the particles and especially in the dense suspension phase, right. So, that is known as interstitial gas which is between the particles or the void space. Then again riser. So, riser is basically known as a in the column where the particles are carried upward by the gas with no distinct bed surface. So, in the riser, say generally the vapor and the catalyst are going up through the riser. So, right, that is why named riser. So, the solids are moving up, gas is moving up, and the contact point, this is the contact point because the diameter of this unit is small, and so there is a good contact between the gas and the catalyst. So, in the riser you will have more and more catalytic cracking when you have the FCC type units, right. So, most of the cracking takes place in the riser part. So, generally the height of the diameter is small, but height is very large, they can be of the order say 10 meters or 15 meter, very large column, right, in terms of, and velocity is high through that. So, the coke formation is to be minimized, especially when you have a higher range of hydrocarbons. And again segregation is another term where in which we define the tendency for the particles to gather in different zones according to their size and ordinary state. So, whatever I was talking in the Geldart chart. So, there will be lump of the particles, a crunch of the particles, and they will be at the localized places in the bed column. So, there will be, so through, and the gas is channeling. So, this is not a desired condition when you look at a good kind of fluid bed reactor design. Then there are some other terms, one is known as minimum fluidizing velocity. So, minimum fluidizing velocity is basically you need to design the reactor or and this will depend on the type of the solid material and the gas. So, basically minimum fluidization velocity as the name says. So, it is the velocity which is required to fluidize the bed, right, or to allow the solids to keep them in the suspended form, because the gravity force is always acting vertically downward. So, to overcome with that, right. So, buoyant force is required, and that is what the superficial gas velocity I was defining. So, depending upon the volumetric flow rate of gas divided by area of cross section of that tower. So, this is known as superficial gas velocity. So, this will happen when your pressure drop exceeds the weight of the solid, and this happens when the gas velocity exceeds the minimum fluidization velocity. So, through your packed bed experiments or fluidization experiments, one needs to calculate the minimum fluidization velocity required for the given size particles in a given column diameter, and then the other things. So, this is based on because what will the pressure drop in the bed at those conditions, right. So, fixed bed, then fluidizing, and what conditions are required to make the bed fluidize continuously, what is the illustration or loss of particles, what is the residence time or hydrodynamic study need to be done, because different size when you have mixture of particles. So, different size particles will have different degree of fluidization, right. So, to what is the suppose there are wide variation in the particle size, then it may not be good, because fine particles will be leaving the bed and larger size or coarse particles will not be able to fluidize under the given velocity condition. So, one needs to design or identify the conditions required to fluidize. And another term is known as terminal velocity. So, terminal velocity, it is for individual particles are blown out of the bed when the gas velocity exceeds, which is known as terminal velocity. So, terminal velocity is basically the velocity at which the particles leaves the bed, right. So, it will again depend on the individual size of the particle and their physical property. So, in lot of applications, if you look at the refinery, petrochemicals or chemical industry or process industry, the fluidized bed columns are being used, right. So, operation is smooth, right. It behaves like a liquid like flow of particles. So, be just like a fluid property what we are talking, which allows the continuous automatically controlled operations with ease of handling. So, the transportation becomes easy, operation control becomes easy when you have a fluid type of operation. And again I told you that solids are moving up and down in this, right. They are going up and they are going down. So, internal kind of circulation is there. So, there will be a good kind of back mixing in this reactor, right. So, rapid mixing of solid leads to nearly isothermal conditions. So, heat transfer, where the heat transfer is an issue, the fluidized bed reactor may be helpful, right. So, throughout the reactor you will have good control of heat, and hence the operation can be controlled simply and reliably, right. And these kind of operations can be done at large operations, but there are disadvantage also, right. The particles, that is, it is very difficult to describe the flow of gas with its large deviation from plug flow. As I said that the fluidized bed reactor generally behaves like a CSTR mixed reactor, right. But we try to, because the CSTR, you know, the conversion will be low, and conversion is low, the productivity will be low. So, what we want to have a more or more plug flow type design. So, it means you need to do the high velocity, higher condition, higher severity of operation, right. So, the plug flow condition, maintenance of that is difficult, right. So, we need to find out the RTD, and then we need to find out what is the exit age distribution of the particle, which you get generally from their RTD study. So, and then you can correlate the actual residence time inside the reactor, and it's not exactly, it's not behaving like a plug flow reactor. So, there will always be a conversion less than the plug flow reactor. So, this is one thing. So, when you try to high velocity, there may be a bypassing of the solids by bubbles, right, there may be kind of channeling. So, some unwanted, because more and more voids will come, right, and the gas may channel through those voids. So, this is again a problem when you try to maintain the plug flow condition in a fluidized bed reactor. And rapid mixing of solid in the bed, right, that leads to non-uniform residence time of solid in the reactor. So, that is again, as I said, there is a kind of degree of back mixing, and there is a downer, and the solids are moving up, they are coming down. So, there will be a kind of a degree of mixing, and because of that there will be always be a non-uniform residence time distribution. So, RTD, which is generally calculated from e to the power minus t divided by t bar, right. So, and integrated to the whole length 0 to infinite something. So, dt. So, that is something the concentration profile needs to check based on the radioactive pressure, and then one needs to utilize that mean conversion which I was talking, right, for the given system. So, that is again an issue here, that your residence time t bar is not a definite, there is a variation in that residence time, right. It may vary depending upon the flow condition. And friable solids are pulverized and entrained by the gas, because when you have very find the particle which is very soft. So, what will happen, it will crumble during the operation. So, attrition, because of the attrition, and it will become finer, right, and then it will go along with the gas. So, there will be a loss of the particle. So, these are some kind of disadvantage, but fluidized bed reactor, as I said, they are widely used. So, one is the solid catalyzed gas phase reaction, they are widely used. So, one of the most important is your FCC cracking, right. So, more than 420 FCC reactors are available worldwide, right, and they are producing a large amount of gasoline from the heavier feedstock, right. So, larger molecular weight hydrocarbons, right, which can be a C20H42, something like a paraffin hydrocarbon, right, crude oil fraction, and that is cracked to a product like C10H22, something like that, right. So, which is towards the gasoline. So, we look at something like C5, the C15 or C18 range of paraffin hydrocarbons. So, by cracking one can do that. So, FCC reactors are widely employed for the production of gasoline, what is called FCC gasoline. So, this is one important application of this fluid catalytic cracking, and since these hydrocarbons tend to form coke or carbon. So, in this kind of unit it is possible to regenerate the catalyst time to time. So, that is again another advantage. So, this is the very wide operation. Then same thing, reforming is done in this kind of reaction, right, plate forming what I was talking. So, different kind of semi regenerative process or continuous regeneration of the catalyst is possible when you have this kind of operation. So, something like a moving bed reactor which was used earlier, and now this is being replaced by this continuous reforming by using this fluidized bed reactor system. Then Fischer-Tropsch reaction also they are looking this kind of system, right, where catalyst is being bubbled or fluidized, or something like the slurry bubble column reactor is generally used to, because it is a highly exothermic reaction, but when it is a fluidized bed, then again the control of heat is better. So, you can whatever the heat which is generating, that can be removed, right, and that is advantage here. Similarly, there are several other process in the petrochemical and pharmaceutical industry. So, where these kind of reactors or fluidized bed reactors are used, like oxidation of sulfur dioxide to sulfur trioxide. Generally, the fixed bed system is used, but reaction is highly exothermic. So, again this fluidized bed reactor can be a better option. Same thing for acrylonitrile and aniline, right, and HDPE, high density polyethylene, low density polyethylene in the petrochemical industry. So, where by polymerization of ethylene, these kind of high density polyethylene, low density polyethylene, polypropylene, these are made, right. So, Ziegler-Natta type catalysts are generally used, and they are in the fluidized bed reactor. So, wide applications on the catalytic as well as non-catalytic also. You can see here roasting of all the ores, blast furnace, right. So, combustion, incineration, coal gasification, right, the coal gas pulverizers, you might have learned about the coal combustion process. So, these are generally done in the case of in the fluidized bed reactor. So, these are non-catalytic type of operations also. Just a typical example which has been taken from the reference, that a simple reactor and regenerator combination, which is FCC unit, fluid bed catalytic cracking unit. So, you can see here that you have a reactor system like this. So, this is your reactor part, and the gas oil which is your feed, right. A gas oil is nothing but the atmospheric gas oil or vacuum gas oil which is obtained from the bottom of a distillation unit, crude oil distillation unit. So, a gas oil comes like this, and you have a regenerated catalyst which is coming from here. So, catalyst circulation rate one can calculate based on this how much temperature is required in the regenerator section. So, you have a fine powder of the catalyst coming from here. So, which may be 100 to 150 to 100 micron or up to 150 micron, and according depending upon the velocity of this. So, this is acting as a gas for fluidization also, that is vapors of the hydrocarbon, right, and sometimes steam is also used to strip out the hydrocarbon fraction along with this. So, this is taken here, and this is your reactor part, right. So, you have the dense bed and dilute phase. So, the product forms, the vapors forms, right. So, the vapors are taken to a fractionator for distillation, but the catalyst is separated here by using a cyclone separator and then taken back into this unit, where the air is used for oxidation, because I told you regeneration of the catalyst is done by burning this catalyst, spent catalyst in the presence of air at around 550 degree centigrade for 5 hours. So, here roughly the carbon reacts with the oxygen and converts it into carbon monoxide, carbon dioxide. So, this is being done and in a regenerator unit here. So, this is along with this catalyst comes here, and since the reaction is exothermic here. So, proper heat control is required. So, sometimes this heat is being transferred here to vaporize the hydrocarbon. So, depending upon the unit, and here it is a cooler for a spent catalyst, which is just to cool it down below, because the temperature should not exceed above 750 degree centigrade here. So, the regeneration is done here, and the whatever the particles they are taken into electrostatic precipitator. So, you can separate along with CO, CO2, right. So, that and unburnt oxygen and nitrogen, right, and the catalyst is taken again here separated and then sent back. So, that is a kind of circulating fluidized bed also catalytic cracking. So, this is very important or wide application in petroleum refinery for the production of FCC gasoline, for gasoline production. The design and the hydrodynamic study, that is when we look at a reactor design. So, in general it is a very simple, you know that we are talking something like a CSTR. If we just simplest case we say, we assume that it behaves if like a CSTR, then one can write simply this thing W by F naught is equal to x upon minus R A, and one can calculate if this is known, right. So, rate of reaction is to be calculated, which will be function of the hydrodynamic, because there will be a mass transfer of the gas, right. So, there may be different phases. So, that is important, that how to find out the rate, but once that is known, then this is simply the mass of the catalyst required for a given conversion x in the given feed rate of F A naught, right. But simultaneously one needs to check the distribution of the particle, because what W we are talking is not a fixed bed reactor, it is a moving bed reactor, and not a moving bed reactor, but the particles are in bubbling condition. So, there will be voids, right. So, we need to look at those conditions, and depending upon that you have to find out the degree of mass transfer and degree of chemical reaction, because every step will have its own resistance. So, overall rate one can write it something like that, minus R A is equal to some constant, right, K dash times whatever the kinetics say, if it is first order with respect to say this, or whatever the nth order C A to the power. But this is not just like the kinetic rate constant, it will be a contribution of the mass transfer resistance also, right. So, that is important, that how to find out this rate of reaction in the case of a fluidized bed reactor, that is one thing. Simultaneously one needs to find out, because this conversion will depend on the residence time, right. So, the smaller particle may spend lower time and larger particle may spend higher time, or depending upon the superficial gas velocity and the size of the particle, there will be a distribution of the particle. So, your conversion will also be a function of residence time distribution, right. If it is plug flow, it is fine, it will be just like tau, right, but most of the time it is not a plug flow condition. So, one needs to find out the mean residence time T bar, and this mean residence time T bar will depend on the age of the particle. So, we need to find out some kind of exit age distribution for each size range of particle, right. So, conversion will be now mean conversion of the solid. So, what I am talking here, this is something like, or if it is a non-cat solid, otherwise it is a conversion of the gas. So, one needs to calculate mean conversion, which is not constant, which will depend on the residence time, that is T bar, right. So, one has to calculate this concentration as a function of time on stream, or the mean average concentration throughout the reactor, and then calculate. So, simplest is one can take a simple CSTR and take the rate equation and can find out, but this is not a correct way. So, the purpose of showing this here is based on that depending upon this superficial gas velocity, right, which is being used to fluidize the solid particles, right. So, that is important. So, this is a superficial gas velocity. So, that is all of you know, this is the velocity if the vessel is empty of solid, right. So, whatever the area of cross section of this pipe multiplied by the velocity, that is known as the volumetric flow rate. So, if you know the volumetric flow rate of gas, or if you know the mass flow rate of gas, so mass flow rate is nothing but density of the gas multiplied by the that is the volume of that volumetric feed rate, right. So, one can very easily find out this thing. So, if I know that diameter of the column, simply d. So, pi d square by 4, right. This is the area of cross section and multiplied by the velocity, and that will be the volumetric flow rate of the gas V g. So, one can very easily find out this superficial gas velocity. So, this is called superficial gas velocity because it is calculated based on empty bed. Then diameter of the particle size, right. So, different size particles may be there, single size particle. So, these are small dots are representing the particles, right, particle size, and their density, both are important as I discussed. Fractions, right, the volume fraction of the solid in bed. So, basically what is the mass of the solid in the bed, or we define it in terms of the volume fraction of the solids in the bed. So, that is again important, and the void fractions, right, volume fraction of the voids in the bed, that is again important, right, in each phase. And this is what shown here, the this is your gas bubble. So, there are gas bubbles you can see here, right, because they are moving up, the gas is moving up, which is surrounded by a solid now, some crunch of the solid particle, and some solid which is there in the different positions, and that is known as kind of emulsion form, right. So, and this height of the bed can be calculated simply from the mass balance, right. So, one is the height of the packed bed, which is your when their bed is not fluidized, right, and when the bed is being fluidized, but mass will remain same. So, one can very easily calculate it based on the solid balance, right. So, something like h into 1 minus epsilon f, if I say h f into 1 minus epsilon f, right. So, this is the fraction, because epsilon f is the void fraction, right. So, 1 minus epsilon f will be the solid fraction. So, h f into 1 minus epsilon f will be equal to h m f into 1 minus epsilon m f, because that is the fraction when the bed is packed. So, that time height will be smaller, right. So, overall mass will remain same. So, this is what the mass balance. So, when you do the modeling or when you design this kind of fluidized bed reactor, so I am not going in detail because that is a chapter course, but very quickly I will just give you some glimpse how what is the approach to design it, right. So, modeling of the fluidized bed reactor means related to something like hydrodynamics, and something is used to find out the overall rate of reaction or resistance which is offered. So, simplest as I said, a combination of the plug flow and a CSTR. So, simple plug flow and complete mixing models, right, they may not be good to define the fluidized bed, right, because there is some kind of back mixing, there is some kind of the plug flow condition. So, exactly by considering it plug flow, that is also not correct, and completely a back mix reactor CSTR is also not correct, because there is a kind of residence time distribution which is between the plug flow and the CSTR, right. So, in general what I discussed is your conversion versus W by F naught curve, right, and you need to look at the degree of back mixing, right, but they are not well to define a plug flow reactor. The reason is that the fraction of the gas bypasses the catalyst, right. So, some of the gas is leaving the bed without contacting the solids, right, and this will happen because there will be pockets of the solid, right, and the gas. So, there are the voids between these solid particles and the gas leaves them, right. So, it may not be good to define it like a CSTR or like a plug flow reactor. So, we need to do hydrodynamics, right. So, hydrodynamic of CFC, this fluidized bed reactor is very important, very crucial to define the residence time distribution, right. So, let us look quickly on that. So, we have to look at the behavior of a rising bubble, because as I said the gas moves up like this, right. So, what is the behavior of this gas, right? It will depend on many factors, right. It will depend on the particles, it will depend on the density, right. It will depend on the size and depending upon the reaction also, kinetics. So, this is the first one which is known as a two phase model. So, there are generally two models which have been used, but this is the simplest one, a two phase model, where we are saying that there is a bubble phase and there is the emulsion phase. So, emulsion phase means solid phase, right, and bubble phase means the gas bubble which has some solid surrounding it, right. So, the experimentally under certain condition this is valid, but most of the time a three phase model which is also known as Cunney-Levenspiel model. So, this is the model which is developed by Davidson. So, sometimes we call it Davidson model also, two phase model, right. So, it simply says that in the vicinity of a single bubble in a fluidized bed, right, which is something like in there is a solid and there is a gas. So, bubble and the emulsion phase. So, solid clusters of the solid I am calling emulsion, which are chunks of the solid, right. So, there is less reaction, but most of the reaction when we are saying the gas, right, which is in contact with the solid and there is a reaction. So, let us just talk on that. So, it says that the rise velocity of the bubble, which is I am defining now u b, which is something like a unit of meter per second, right. So, this will depend on the bubble size. So, these are the just your hydrodynamic correlations and the mass balance and the force balance equation, one can calculate this. So, the bubble size is important, velocity of the bubble, right. So, that is very important because the bubble size will decide the rise velocity of the bubble. In the bed, at what velocity the bubble is going up, because residence time of the gas bubble is important, and for how much time that gas bubble is in contact with the solid will decide the conversion or average conversion. So, that is important, right. So, the gas behavior in the vicinity of the bubble depends on the relative velocity of the rising bubble and the gas rising in the emulsion. So, gas is in the emulsion phase, gas is in the bubble phase. So, let us see that. So, this is what the picture of a bubble, right. So, here we have a bubble. So, this is a gas bubble, the white one is showing a gas bubble which is surrounded by a solid. So, basically this is a 3 phase model, but very easy to understand, and then one can convert it into 2 phase model. So, you have a bubble here, you have a cloud. So, we are calling the film, the solid is the bubble is surrounded by a solid, thin film of the solid, and here you will have, we will have more reaction because there is a good contact between the gas and the solid. So, this is the bubble, this is your cloud, here is again is some more crunchage of the solid. So, basically this is known as a wake phase, another phase, right, and this is the where the gas is low or some stagnant gas, and this is known as emulsion phase here, right. So, now we have mainly, if I say the 2 phase, then there will be a bubble and the emulsion. If I say 3 phase, then there will be a bubble, then there is a cloud and then emulsion. So, cloud and wake, these two are combined together. So, bubble phase, cloud and wake phase and emulsion phase. So, that is known as a 3 phase model. So, what is there in fine particles bed, your u b, which is the velocity of the bubble, is much more higher than the emulsion phase velocity, right. So, fast bubble and clouded bubbles here, something like that, right, the bubbles are moving up. Wherever when the particle size is larger, then bubble velocity is smaller, right. So, it will depend on the particle size, and your bubble velocity is smaller than the emulsion velocity, right. So, these are I am not going in detail of that, but what I mean to say when I discuss a fluid bed reactor. So, we are just trying to visualize it something that what is the degree of mixing, what is the mass transfer in each zone, and what is the chemical reaction contribution, and that will decide the overall resistance, which may be a combination of some are in series and some are in parallel. But just as simplest, what we have assumed that there is a bubble, something like a bubble, this is a gas bubble, on this there is surrounded by a film of the solid. So, there are solid particles around this, right, and there is some kind of wake. So, because this is here at this point you will have something more concentrated solids here. So, this is known as a wake here, wake phase, and then outside of this bubble, this is something like a emulsion phase. So, this is your bubble and this is your emulsion when I say a 2 phase model, right. And this is what the complex series parallel resistance to mass transfer. So, when you have a packed bed reactor, you can easily eliminate these mass transfer resistances, but when you have a system like a fluid bed reactor, the system in that system it is not easy to eliminate them, right. So, one needs to control them, but if it is a plug flow, of course, we can minimize them under the plug flow condition. So, basically a complex series parallel resistance to mass transfer and reaction. So, we have a reactant A in bubble, that is what I said, that reactant A in bubble, it will react because it has a solid surrounded, right. So, there will be some reaction, there is some concentration of the solid. So, depending upon that there will be some reaction in the bubble, right. The rest which could not react, it will transfer to the cloud. So, this is something here, the bubble. So, there is some solid here, there will be a reaction and rest will transfer to the cloud phase. So, again in the cloud phase we will have some reaction in the cloud, and then which is not reacted, it will transfer to the emulsion phase, and finally, the emulsion phase there will be nothing to transfer. So, whatever there, that will react in the emulsion phase. So, we have now a combination that is in series. If you look at this side, it is in series, and a combination of series and parallel. So, mass balance one can very easily write whatever input here, that is transferred to the cloud plus reacted, whatever input here, that is transferred to the emulsion and reacted, whatever here, that is transferred to the product. So, that is a very complicated series parallel reaction is used to find out the overall rate of reaction. So, if I just talk only a two phase model, so in the two phase model we just talk a cross section of the bed which is taken either by the bubble or by the emulsion. So, what fraction has been taken by the emulsion phase and what fraction of the bed has been taken by the bubble, because we are not considering any other phase, right. So, for this is one parameter, the fraction of the bubbles, right, in each phase. Then second, interchange coefficient, because there is a cross flow what I discussed here. So, there is a kind of cross flow, transfer and chemical reaction. So, it means the interchange coefficient, right. So, that is from bubble to emulsion, how much is the mass transfer and how much is the reaction. So, interchange coefficient, that is the second parameter, and third is the axial effective diffusivity in the emulsion phase, because the reaction will depend on that effective diffusivity of this gas into the solid. So, that is again important here. So, it is basically there are three parameters when you look at a two phase, and this is what is shown here. So, when a actual picture is different, but when we are assuming a two phase model. So, we have a bubble phase, we have a emulsion phase here. So, something is coming here in terms of the concentration or mass, right. So, one can very easily write a mass balance here. So, which is partly, so this mass gas is going partly into the bubble phase and partly coming into the emulsion phase, and then when it leaves, so part of the concentration is coming from the bubble phase CAB out, and part of the concentration is coming from the emulsion side, right, of a concentration of gas A in the bubble, concentration of gas A in emulsion, and then this is coming at the exit. So, we get the average concentration. So, we have modeled it like this, but so this is your black box where you need to evaluate the parameter and to match it with this is your input and this is your output, right, and that will decide your conversion, whatever CA bar by CAI, or one can calculate the X or mean conversion based on that. But actual conditions inside the bed will depend on the gas velocity, superficial gas velocity, density of the solid and size distribution in the of the solid. So, just if you look at here the two phase model. So, in this the fraction of the total flow rate through the bed is considered to be in the bubble phase and rest in the emulsion phase, that is what I discussed, and between both phases there is a certain interchange or cross flow. So, it is a kind of transfer coefficient, we need to calculate that either from some empirical correlation or some from the hydrodynamic condition. So, it is a kind of mass transfer coefficient or overall transport coefficient which can be determined, right, experimentally or from the model, right. So, at the outlet both streams with their respective conversions are hypothetically mixed to give the exit stream with its mean conversion or concentration. So, this is what I was discussing in the here, right. So, all these are discussed here. So, since there is no reaction, so we assume that there is negligible reaction in the bubble phase in the two phase, and because of it the high velocity the flow through that phase can be taken to be of the plug flow. So, bubble phase is assumed to be plug flow but in the emulsion phase the various degree of deviation from plug flow can be postulated, because the solids are moving up and down, right. So, there is a kind of back mixing in this. So, that cannot be considered as a plug flow. So, cross section from bubble to emulsion transport, right. The cross section of the volume fraction of the bed occupied by the bubbles is derived from the observation that essentially all gas flowing through the bed in excess of that required for the minimum fluidization goes into the bubble phase. So, basically what you get, that you get from the minimum fluidization condition, right. So, gas flowing through the bed which is in excess is nothing but what goes to the bubble phase. So, basically when you write a mass balance, so everything is calculated above this, that is u b minus u m f, or if I calculate some velocity, right, in the bubble or in the cloud phase. So, whatever excess of the minimum fluidization, that will go into the, that is through the into the bubble phase, right. So, that is one essence, that the mass flow rate which we are calculating, or volumetric flow rate which we are calculating from the bottom of the column in terms of the superficial gas velocity, and that is allowing the bubble to rise, right, and that will happen, bubble will rise only when it exceeds the minimum fluidization velocity, right. So, that is what the bubble rise velocity also we have to define accordingly in this, right. So, I am not going in detail of that, but one should have some idea when he looks for the fluidized bed type of reactor design, and details can be in the subsequent courses. The fraction of the bed volume in the bubble phase can be derived from the bed heights and the void fraction at the minimum fluidization and flow rate. So, basically it is a mass balance. So, you know that the fraction of the solids in the bubble phase, fraction of the solid in the emulsion phase, right, and if there is some other wake phase. So, all these will be total fraction of the void fraction of the bed. So, one can total fraction of the solid in the bed. So, one can calculate that simply, right, and same thing the height of the bed which I was talking, the fluidized bed height. So, minimum fluidized bed height and related to the void fraction of the bed. So, it is just a mass balance for the solid, right. So, one can calculate that. So, a fraction of the bed volume in the bubble phase can be derived from the bed heights and the void fractions which is at the minimum fluidization and the flow rate considered at that point. So, this is simply written here in terms of that pi r square L, right. So, this is the radius of the bed or diameter which I was discussing, pi d square by 4 into L, which is the height of the bed, right, height of the fluid bed. So, this is nothing but the volume of the bed, right. So, when it is fluidized, and pi r square L 0 if you say, this is the height of the fixed bed or a packed bed when it is not expanded. So, area is same, height is now h 0 or L 0, right. So, this is the initial volume, and whatever the rise, that will be in terms of the how many bubbles have come, because the bed is rising, because in between in the interstitial space there are gas bubbles now. So, nothing but pi r square L, which is now the volume of the bed, right, in the fluidized condition, times whatever N b, which is nothing but representing the number of bubbles per unit volume multiplied by the average volume per bubble. So, basically bubble volumes, right. So, pi r square L into N into V, where N is the number of bubbles per unit volume of the bed and V is the average volume per bubble. So, this product will give you the total volume of the bubbles, right. So, that is nothing but expansion there, which has arrived, or bed height has been increased because of these gas bubbles. So, simple material balance or a volumetric balance in terms of the bed height. Some salient again features when you look at the design, the interstitial emulsion phase flow, right, V 1, that pass at velocity close to the minimum fluidization velocity, right. So, because I told you that in the emulsion phase the solids are together all together, in the bubble phase the gas is there, right, more gas, right, and reaction is not with the solid, reaction is when the gas contact with the solid, right. So, this is one important thing when you have a 3 phase model. So, more reaction is in the bubble phase, right, bubble phase, cloud phase, because it has the solid and the gas, right. Rather in the emulsion phase, the solids are more, right, the gas is just at the almost 0 velocity there, right. So, this is one thing, that interstitial emulsion phase flow V 1, right, at velocity close to the minimum fluidization velocity through the space between the fluidized particle, while the excess flows in the form of rapidly moving voids or bubbles which are essentially free of particle, right, and grow by coalescence as they rise through the bed. So, when the bubbles move up, they will now increase in the size. So, that is size, they are growing in size, right. The bubble size is increasing when it goes up. So, this is one thing when you look at the velocity V1 or interstitial velocity in the emulsion phase. Second thing is the bubble phase, right. The bubble gas phase, this does not make good contact with the solid, right. So, reaction in the bubble phase is inefficient in the two phase case, and the gas which is flowing interstitially is in intimate contact with the particle, and if chemical kinetics are favorable, the efficiency of chemical conversion in this phase will be high, right. So, that is again the within the particle interstitially the gas which is present between the particles. So, there if the kinetics is favorable, temperature is okay, then the reaction will be in the interstitial space, that is where the gas is there and solid is there, right. And exchange between these two phase is determined based on the size of the bubble, and it decrease as the size of the bubble increase. So, this is what I was talking, I have already discussed, and this is what the modeling when you do. So, you have a two phase flow system, the V1 is the flow towards the bubble and V2 is towards the emulsion phase. This is the volume V1 volume in the bubble phase and V2 is the volume. So, what the whole system has been just divided into two phase, right. So, one is your bubble phase, another is the emulsion phase, and there is a interchange of mass between the two, right. So, cross flow what we are talking. So, this is a cross flow. So, flow splits into two, bubble, emulsion, and this is something like a plug to mix flow. So, you will have something like d upon UL, a kind of dispersion number, and this is again a plug to mix flow. So, again here you have a kind of degree of non ideality, that is a dispersion, right. So, fraction of the solid we are assuming here is m1 and fraction of the solid in this section is m2, and then these two are taken together what has been discussed earlier, and then again it is a concentration at the exit. So, something is in here and something is out here, which is defined in terms of the inlet and exit. So, one can calculate the conversion, right. So, this is the simplest model, a two phase model, and which is actually shown here. As I told that bubbles go, as the bubbles go up and up, the size is growing, right, and this is your emulsion phase here, and then there is a cross flow here. So, bubble and then this is the K here, which is a cross flow coefficient, right, and that is the whatever the gas which is in the interstitial space here, that is reacting and transforming into the product, right. So, this is what. So, this is for the two phase model, and so due to the shortage of time I have to just close this, and maybe in my last lecture I will just discuss briefly this and some other points for the heterogeneous catalytic applications, and then if time permits then I will just look at some application in the refined and petrochemicals. So, with this I close it today here, and thank you for your attention.